video, we'll see the implementation of the binary search tree. In the binary search tree is a binary tree only. For example, tree is an example of tree with restrictions. A node can have a maximum of 2 children. It is said to be binary tree. On binary tree, if you put a condition that with condition, then we'll get a binary search tree. So what is this condition? For every node, left nodes be less than parent, and right node, that is right hand side node, should be greater than parent. So this is what the condition on the binary tree, so that it will get the binary search tree. Now what I will do is I will develop a program for as usual, we'll include the file. We need to create a node. So this is this is a node structure what we can create, and struct node star root null. The root value is going to be initialized to. Now we need to check whether the node is or root tree is empty or not. It is empty. This is the function. Next, the important functions that can be defined on binary search tree are: one is insertion. Void insert of. So in order to insert, we need to have root value integer value. So for this so this insert node function will make use of this insert function. This is void create node. So void insert node. This is the create node. So we'll define one by one. Insert node, create node. This is as usual how we have created node in the single linked list in the same way. Here, I am Next we'll define this insert node called insert node of integer value. So whenever the node is to be inserted, here we can call insert of %root comma value. So here we need to define this insert function called insert of node star star node comma integer value. So here we need to check node star temp is equal to null. Then temp is equal to star node. If star node equal to null, then that is the starting node to be created. Star node is equal to create node of value. This means if there is no node exists, the whatever the node that newly created is the available node. For example, if the inserting element is less than the parent or temp data, then it must be inserted at the left side. If it is greater than, then it must be inserted at the right side. So in order to do that, we will compare first. So else if value is less than temp data, then we must insert this at the left side. So insert so temp left, and we need to pass the address of temp left comma value. So we are making use of the recursive functions here. Else if value is greater than temp data, then we must insert it at the right side, temp right comma value. This is also we are going to do in the recursive way. Otherwise we can say that some duplicate element has come. Duplicate element. So we are not going to do any insertion here. So we have done the insertion. Then we need to print this tree. The tree can be printed in several ways, either via in-order, so either via in-order or pre-order or post-order. Void pre-order or void post-order. So three traversals are there. This is three traversals. So in-order means here first we're going to visit left, then parent, then right. In case of pre-order, first left will be visited, next right will be visited, next parent will be visited. Pre-order means first parent will be visited, next left will be visited, next right will be. In the post order, left will be visited, right will be visited, next parent. Now what I am going to do is I am going to define the in order sub node star node. So as usual, we'll take a temporary node. Temp is equal if temp not equal to null, because we should not work with the root node. That is the reason we are creating a temporary node. We are making use of temporary node and doing it. So in the in order traversal, first left subtree will be visited. Next, the parent. Next, write subtree. So we are going to make use of the recursive function temp left. Automatically, it will go into the left side. Printf %ld comma temp data. Now the parent value will be printed. Next, we need to move on to the right side. Temp. So this is the way how the printing will take place. Same way in order. Next is pre-order traversal. Same thing. That will copy paste and rename this in order to pre-order. So in this pre-order, first parent will be visited. First parent will be visited. Next left will be visited. Next right will be. Next, in the case of post order, we are going to define the function post order. Post order. This first left will be visited. Next right will be visited. Next parent. Now that will see whether this in order, pre-order, post order are working fine or not. Void main. So first we will need to insert the node. Insert node. So as I am typing this function, you draw a binary search tree. So insert node. First node to be inserted is 6. Next insert node. The inserting of the node is the first 6 will be inserted. Next insert 2q. Next 1. That means 6 left side is 2. Next its left side is 1. Next insert 8. Next we'll insert 5. Insert 3. Insert 2. 2 or let us say 4. So now to have the display correctly, the percent backslash n in order. So let us see what is the output we'll get. So I hope you might have drawn the binary search tree. 6, 2, 1. For 6 right hand side 8. For 8 left hand side 5. And 3 is the left of 5. And 4 is the right of 4. So here in order of root. So 1, 2, 3, 4, 5, 6. This is the in order traversal. So whenever you perform the in order traversal on the binary search tree, the elements will be printed in the sorted order. So in order traversal, elements will be printed in ascending order. Next printf ascend preorder of root. Next post order of root. So 1, 2, 3, 4, 5, 6, 7, 8. 6, 1, 2, 3, 5, 6. 1, 2, 3, 4, 5. 86. So visiting of parent, that is according to in-order traversal, parent, in-order traversal left, parent right, pre-order traversal parent left right, and post-order traversal left right and parent. Anyhow, while inserting these nodes, you might have generated the tree and run the insert in order traversal on that, and pre-order and post-order traversal, and compare the output. You will get the same output. So construct the binary search tree and search for the in order perform the in order traversal, so that you will get the elements in the ascending order. Okay. Then how to find the minimum element and maximum element? So other operations on binary search tree, other operations, find minimum and find maximum. Find min, find min, and find max. So in order to find the minimum, so we need to have the help of root. So here in find min, struct node, star node. So as usual, we'll take the temporary value. Struct node star temp is equal to temp is equal to. First, we need to check whether the node is there any node available or not. So if node equal to null, then we cannot print anything. So that will give a temporary or an error code like this. If node equal to null, then return 999. Or we can say instead of node, we can say temp, because we have assigned to temp. And one more thing is we need to go through recursively to find the minimum element. Next thing to be checked is whether this temp is having left side or not. If temp left is equal to null, then obviously temp data is the minimum element. Else return find min of temp left. So now here what I'm doing here, we are going to search it recursively. Now the temp left will be placed, temp left will be assigned here. If temp left is equal to null, then return this. Otherwise, if temp left if temp is equal to null, then it will return the minus 999. Otherwise, if temp left is equal to null, it returns the temp data. So this is the way we will get the minimum element from the binary search tree. Now we'll write this printf minimum element in PST %id find the min of root. So the minimum element in the binary search tree is 1, because this is the one which is at the leftmost side. So in the same way, we'll also define the find max. Here let will replace this into max. So in order to go for max, maximum element, we need to go for right side. Find max in capital temp. So Just by changing this left to right, we'll get the rightmost or the maximum element in the binary. Here maximum element, find max. So you can say what is the maximum element out of this 8. 8 should be the maximum element. We must get 8 as the output. The maximum element in binary search tree is 8. So find min and find max is also completed. Next we'll move on to the important function in the binary search tree is removal. This removal of nodes. So remove node of value or input. So it is making use of another function remove node star int. So in binary search tree, removal operation should be taken very carefully. We need to do the removal operation. Now we'll define the removal of a node from the binary search tree. Void remove node of value. Here internally all root comma value. Here instead of void remove of node star. So as usual, we'll take a temporary pointer. Temp is equal to star node. So in the case of removal, we need to take care of the 3 points. One is removing a leaf node, removing leaf node, removing node with one child, removing node with two children. So these are the 3 things we need to consider in this. For example, if there are no elements in the tree, then simply return temp equal to null, return. To remove an element, first of all we need to check whether the value is less than temp data or not. If value is less than temp data, then we need to remove by moving to the value is less than temp data, then we need to traverse to the left side of the tree for the removal. Temp left comma value. If value is greater than temp data, then remove. We need to move our traverse at the right side, and we need to do value. So let us include the else part. If temp is equal to null, then simply return. Else, if value is less than temp data, remove node and move to the left direction and remove the node. If the value is greater than temp data, then move the traverse to the right hand side and remove the value. And else if value is equal to what is the value? If the value is equal to temp data, now here 3 cases will come. One is if that particular node itself is the leaf node. That means if temp left is equal to null and temp right equal to null. That means if both the left child and right child, that means there is no right and left child, then temp is equal to null. Temp is equal to null. Or we can say temp is equal to null and free of temp, we can say, and return. That is if both have no, that is if the node have no children. In the tree that we constructed, uh, whenever you construct then binary search tree with these elements, then 1 will be the node with no children, and 4 will be the node with no children. So what we will do is I will remove node 1, and we'll see whether the node 1 will be is removed or not. So it is executed without any error. So I want to know whether the 1 is really removed or not. So for that I need to go into in-order traversal so that I can come to know whether 1 is a element removed or 1 is a node removed from the tree or not. So here 1 is printed. That means it is not removed from the. Here we'll make a small change here. Instead of temp is equal to null, we'll make star node is equal to. So when we make star node is equal to null, the actual reference will become null because we are assigning to temp. Temp is equal to null means it won't give you any thing because we are sending ampersand root. So directly we are going to. It is better to make change with the star node itself. Now we'll see whether will it work or not. Yeah, the remaining elements are 2, 3, 4, 5, 6, and 8. So after removing the node, removing the node 1, we have printed the in order of root so that we got. And one more child node is 4. Another child node is 4. So let us see whether this 4 will be removed or not. Well, 1, 2, 3, 4 is missing. That means 4 is removed, which is the child node 5, 6, 8. So the first case, a node without having left and right child are immediately removed. This is fine. Up to here, the code is working fine. So this is for the case node with no children. Next is we'll go for node with one child. Either it is left child or right child. If before going to this, let me go for node with two childs first. Node with two childs. If temp left not equal to null and temp right not equal to null. So in this case, both the left child and right child is available. In this case, you can replace the largest element from the left hand side. You can go to the left hand side and get the largest element and keep it as the node which is going to be deleted, or you may go to the right hand side and pick up the smallest element and keep it as the node that is going to be deleted, then traverse at the right side and delete the minimum element, or traverse at the left side and delete the maximum element. Anything you can do in this particular case. So it depends upon the programmer how he will implement it. So currently what I am doing is I am going to pick up the minimum element from the right hand side and keeping it into the node where it is going to be deleted. So find min of temp right. So from right side, whatever the minimum element is there, that minimum element we are going to get it. So once we got into temp data, then what we are supposed to do is we need to remove the right hand side value. We need to traverse to the right side and remove the data which is minimum, that is temp data. So this is the case of node with both left and right child. In the tree that we have constructed, 6 is the root node which is having both left and right child. Now what I will do is I will remove the node 6 and we'll see the in-order traversal, whether this will print the in-order traversal will print the elements without 6 or not. So 1, 2, 3, 4, 5 is there, 6 is missing. So which means that there is no 6 in the tree. That means the root node 6 is removed. So our left and right child, the node with both the children, removal is successful. So now we'll move on to the else part. If not these things, you can also place else if here, else if part also we can write here, stuff is there, that is else if. So in this else part, we'll see node with left or right child. For example, if a node is having only left child, then we need to attach the left child. Otherwise, if the node does not have the left child, then we need to attach the right child. So for that, I'm taking a temporary node, and this TT is star node. That is what the current node which is to be removed. Now, what I'm doing is star node is equal to, if the star node have left side, that means if the left of the current node is not null, then we need to assign star node left. Otherwise, we need to assign star node right. So now we replaced the node with the either left side left value or left node or right node. That is left child or right child. Now since we have replaced it, just we'll remove TT and we can write printf percentile D or the node percentile D is removed. What is the value? Is going to be removed. Now, one case is there which is the element 3. Element 3 is having the right hand side value, that is 4. Let us see by removing 3 whether the this code is going to be executed successfully or not. Well, in the resultant output, 1, 2, 3 is missing, 4, 5, 6, 8. So that means 3 is removed successfully from the binary search tree. So with this we have done the operations such as insertion, in-order, pre-order and post-order traversal, finding the minimum, finding the maximum element in the binary search tree, removing of the node from the binary search tree. While removing node, we have taken the help of the recursion, and whenever the value is equal to the data that what we are going to search, we are supposed to go for 3 conditions: node with no children, node with 2 children, and node with left or right child. So far we have done the creation, removal of node, finding the largest number and finding the minimum number, pre-order, in-order, and post-order traversal. Now let will go for collapsing the tree. That means we are supposed to remove all the nodes in it. So void collapse, collapse, void tree of because we require the root node address to collapse the tree. So first we'll define the function void collapse in this collapse tree of root. We need to collapse the root node. Now we'll define the collapse tree of struct. If node not equal to null, then go through the left side, collapse tree of node left, collapse tree of node right. So once you go for left and right, then pre temp, pre node, then finally node is equal to null. So this will collapse the entire tree. Now we'll see whether the tree is collapsed or not. Collapse, and we'll run the in-order traversal. If the in-order traversal won't print any element, then we can say that the tree is collapsed. So this is the previous in-order traversal. After that, nothing was printed. So the tree was collapsed. This is the way how the collapsing will be coded. Next, we'll do the searching operation. For that, we need to write a function. Collapse tree is over. Next, search operation. So search operation will give us binary search. Void search of struct node star, that is the node and int value. So we need to search one element, whether the element is available or not. So what we can do is search node of and search of command. Write a function search for search node of int value. Then what it will do is it internally uses the root and take the value and will define will search the tree. Here, since we are doing only the traversal, so we no need to go for double pointer here. Just it is only traversal. So void search of struct node star node comma digger value. So we may use a temporary pointer struct node star temp equal to null. Temp is equal to node If temp is equal to null, then simply return. Else if value less than temp data, then search temp left comma value. Else if value is greater than temp data, then search at the right side. Else if value is equal to temp data, then print the element percentage d found. What is the percentage d value? And simply return. Else simply break. Nothing. So this is the searching of the node. Now let will go for searching an element. So remove node. After remove node, can use search of. So here node 3 was removed. We'll go for searching of node 4. Search of SEARCH. Here we need to use search node of 4. So element 4 was found. The element 4 found. So that means the element was found in the search operation. So this is leading into the binary search. So all possible operations of binary search we have completed. Now your task is download this code and develop a full-fledged code in the main method for inserting the number of elements, as many number of nodes by the user by using simple do while statement. So this is the end of the binary search tree implementation.